The Internet operates on legacy communication protocols that were engineered for speed and efficiency, not security. When these protocols were designed, they operated under a strict assumption that any device connected to the network was authorized to be there, seamlessly mixing legitimate traffic with unauthorized data. To map the specific attack surfaces where this built-in trust is exploited, network engineers use the OSI, or Open Systems Interconnection Model. The OSI model is a conceptual framework that standardizes how data moves across networks by dividing communication into 7 distinct layers. Attackers target vulnerabilities at each of these levels, particularly Layer 2, Layer 3, and Layer 7. Each layer in this stack relies entirely on the integrity of the layer directly beneath it. If a malicious actor compromises the local hardware connections at the bottom, any cryptographic security applied to the application data is completely bypassed. We will examine exactly how this exploitation works across the stack. We will analyze hardware manipulation at Layer 2, global routing deception at Layer 3, and targeted resource exhaustion at Layer 7. Securing a network is impossible without deploying mechanical, layer-specific countermeasures that explicitly verify the traffic moving through each individual stratum. At the base of our targeted stack is Layer 2, the data link layer. This is where local area networks operate, using switches to forward frames of data based on MAC or Media Access Control addresses, which are unique hardware identifiers assigned to network interfaces. This diagram shows how a switch tracks these addresses using a CAM table. A CAM, or Content Addressable Memory Table, is a dynamic database inside the switch that maps incoming MAC addresses to the specific physical ports where those devices are plugged in. Because physical memory is finite, this table has a strict capacity limit. In the MAC flooding attack, an adversary injects thousands of randomized, spoofed MAC frames into the switch in a matter of milliseconds. Once the CAM table is completely full, the switch cannot record any new, legitimate MAC addresses. To prevent the network from halting entirely, the hardware is programmed to enter a fail-open state. In a fail-open state, the switch abandons targeted forwarding and simply broadcasts all incoming traffic out of every available port. It degrades it to a basic network hub, allowing the attacker to passively intercept and sniff all data moving across the local network. By exhausting a hard-coded physical memory limit, an attacker breaks the isolation of the local network and forces the hardware to distribute sensitive data directly to them. Another structural vulnerability at Layer 2 involves ARP, the Address Resolution Protocol. ARP is a protocol used to map an IP address to a physical MAC address so devices can communicate on a local segment, but it contains no native mechanisms to authenticate the responses it receives. This diagram shows the topology of an ARP poisoning attack. The attacker positions their device logically between a victim network node and the main network gateway, intercepting the communication path. The attacker executes this by transmitting a gratuitous ARP message. A gratuitous ARP is an unprompted broadcast that forces receiving devices to update their internal IP to MAC mappings, even if they never requested the information. The attacker sends these messages to both the gateway and the victim, forcing the victim's cache to map the gateway's IP to their MAC address. This image illustrates the exact structure of the ARP frame where this deception occurs. The attacker simply overwrites the sender hardware address and sender protocol address fields with the spoofed routing data before transmitting the payload. This image details another unauthenticated sequence, DHCP, or the Dynamic Host Configuration Protocol. DHCP automates the assignment of IP addresses to devices joining a network through a 4-step broadcast exchange between the client and the server. A DHCP spoofing attack exploits the timing of this exchange. A rogue device on the same local segment listens for the client's broadcast and rapidly replies with its own malicious offer. If the attacker's reply reaches the client before the legitimate server's response, the client accepts the rogue IP configuration. Layer 2 protocols operate strictly on a first-come, first-served basis. Without built-in cryptographic verification, the network blindly accepts routing instructions from whoever answers a broadcast first or loudest. Moving up the stack, we reach Layer 3, the network layer. This layer handles the routing of traffic across interconnected wide-area networks, utilizing the Internet Protocol, or IP addressing, to send packets globally. This diagram shows the mechanics of IP spoofing. An attacker modifies the source IP address in the header of their data packet to impersonate a trusted internal device, allowing their traffic to bypass access control points that filter strictly by IP. On a global scale, Layer 3 traffic is directed by BGP, or the Border Gateway Protocol. BGP is the routing system that manages how packets are transmitted across the vast autonomous systems that make up the Internet. BGP relies on TCP port 179 for establishing connections. TCP is the Transmission Control Protocol, a standard that ensures reliable data delivery. Historically, BGP lacks native cryptographic authentication for the route advertisements it processes. Attackers exploit this by executing BGP route origin hijacks. They inject bogus routing tables that advertise shorter paths to specific IP blocks. Because BGP defaults to the most efficient route, global traffic is automatically redirected away from the intended destination and into the attacker's infrastructure for eavesdropping or blackholing. Once Layer 3 is compromised, local network perimeter defenses fail. The core map of the network is rewritten to funnel data precisely where the attacker dictates. This architecture diagram highlights the server farm at the bottom, which represents our target as we ascend to Layer 7, the application layer. This stratum governs how software servers process user logic and access backend databases. Unlike lower-level exploits, Layer 7 attacks do not rely on malformed data packets or spoofed headers. Instead, they weaponize perfectly valid HTTP, or Hypertext Transfer Protocol requests. This visualization shows how an HTTP flood attack creates an asymmetric workload. It is a DDoS, or Distributed Denial of Service attack, where the attacker uses minimal network bandwidth to send requests, but forces the target server into maximum resource allocation to answer them. These floods typically use either GET or POST requests. A GET request asks the server to retrieve static content, like an image or a style sheet, which induces a relatively low processing load per request. An HTTP POST flood is significantly more destructive. POST requests require the server to process incoming data, execute backend application logic, or perform complex database lookups. This exponentially increases the computing cost required to handle each individual request. Traditional firewalls and encryption protocols fail to mitigate this threat. To the network infrastructure, these POST requests appear identical to legitimate user traffic. The processing cost itself is the weapon used to take the server offline. Network security cannot rely on native protocols. Defending these systems requires layering strict dynamic verification over unauthenticated infrastructure. This diagram illustrates defensive overlays on a network switch. Port security restricts input by verifying MAC addresses at the physical edge. DHCP snooping drops malicious offers, building a trusted IP to MAC database. Dynamic ARP inspection references this database to validate ARP packets, neutralizing man-in-the-middle attacks. Lastly, IP Source Guard relies on this table to filter source IPs, blocking Layer 3 spoofing at the hardware interface. Higher up the stack, Layer 7 attacks require entirely different mitigations. Stopping an HTTP flood relies on WAFs, or Web Application Firewalls, and progressive traffic profiling to meticulously differentiate malicious bot requests from genuine human users based on their behavioral patterns. True network security is a strictly architectural endeavor. You can only protect the high-level application data if you have absolute verified control over the physical links and network routes beneath it.